Hello everyone. Today we're going to be looking at acceleration. Specifically, we're talking about something that's moving with a constant acceleration. But before we do that, let's recap our old model, something that's moving at constant velocity, because a lot of the skills that we learned from there will apply to this as well. So let's put our moving man at -10, and let's give him a velocity of 2 meters per second. So now when I hit play, we see the moving man start moving, and he's moving at a constant speed. Velocity is not changing. I'll stop him before he runs into the wall here. So we see our position versus time graph is just a straight line. The slope of that position versus time graph gives us our velocity, which we can see is constant. Speed does not change. We can also look at this in terms of a motion map. So if we've got an object at constant velocity, each dot on the motion map represents its position, and we can also put the object's speed in there. So here I've got a velocity vector that shows you it's moving that much that direction, or that fast in that direction. So now if we look at this just a second later, we see the object has moved from here to here. So position is actually represented by position on the page, but our speed stays the same. And as this thing keeps moving, what we see is that the distance between subsequent positions, so remember this is at, say, 0 seconds, this is after 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, and so on, the amount of change in position is the same every time, and our speed stays the same. That's what it means to stay at constant velocity. Now we're going to look at a situation that's not like that. So I'm going to reset my moving man. I'm going to put him at -10. And this time I'm going to leave velocity at 0, but I'm going to give him an acceleration of 1 meter per second squared. Acceleration is a way of describing the change in velocity. So acceleration is really how much velocity is going to change in a given amount of time. 1 meter per second squared, another way of saying that would be 1 meter per second, tells us that for every 1 second of time that passes as the moving man is moving, his speed will increase by 1 meter per second. So let's go ahead and take a look. Notice he starts out slow, and now he's getting faster and faster and faster. And let's take a look back through all our graphs. Now, position versus time we're used to seeing as a straight line. Not anymore. If an object is accelerating, the position versus time graph will be a curve. And we'll see the reason for this when we look at our motion maps here in just a moment. We said that the acceleration was causing an increase in velocity. So this means that for every 1 second that passes, our velocity increased by 1 meter per second. And you can see that in the graph. As time passed, the velocity increased. Now here's an interesting thing. Our acceleration was 1 meter per second squared. So for every second that passes, velocity increases by 1 meter per second. 6.3 seconds went by, and our velocity is roughly 6.3. So you can see that direct correlation there. Let's look at this on a motion map now. So remember, this is for an object at constant acceleration. So we've added another vector. We have an acceleration vector here. And as we cause the object to move, so now we look at it at the next time interval, we can see that the velocity vector has gotten bigger. In fact, it's doubled in size from 1 to 2 because our acceleration is causing an increase in speed. Now if we look at the third point, we start to notice something weird. There's this big gap in the motion, or in the position. So it starts off with this small interval, and then the next one is this much bigger jump. Because it's moving faster here, it covers a greater amount of ground. So as this thing goes on, the distance between two subsequent points is going to increase dramatically. In fact, it increases with the square of the time. So what that means is you take whatever distance is here, once twice that amount of time has passed, 4 times the change in position will have happened. When we go to a third time out here, it'll be 9 times this change in position. 3 squared is 9. And so if we look at the next one, we can see that the gap has gotten even bigger. So as this object continues moving, the difference in position will continue to grow and grow. Notice acceleration is staying the same and velocity is increasing. Now let's look at a couple situations where this gets a little more complicated. Let's take our moving man. I'll reset all of this. I'll put him at -10, -10, and I'm going to give him a velocity of, we'll say, 5 meters per second. And now I'm going to give him an acceleration that's negative. We'll say -2 meters per second squared. Now remember that a negative sign just means that the object is going, or that whatever we're talking about that has the negative sign is going in the opposite direction. So here velocity and acceleration are in different directions. Our velocity is in this direction, towards the right, because that's the positive direction. Our acceleration is to the left. That means that initially the moving man will slow down, and then once his velocity drops below 0, he'll actually start moving the other way. Because remember, this number here, the -2 meters per second squared, simply means that for every second that passes, the velocity is going to decrease by 2, or increase by -2, however you want to think about it. So let's take a look at this motion. So notice again that the velocity is just a straight line, and in fact that the slope of that line is equal to our acceleration. So this has a slope of -2. Notice again that characteristic curve of the position versus time graph. And if we were to calculate the slope at any given point, it's going to be constantly changing because our velocity is constantly changing. So here you can see a negative acceleration. I'm going to reset this and actually show it with vectors on there so that you can see the acceleration and velocity pointing in different directions. Sometimes that can be pretty helpful. So when I say show vector, that red arrow there represents the velocity, that green arrow represents the acceleration, and here you'll see that the velocity arrow will constantly change, that acceleration vector will not. And notice that the rate of change of that velocity vector is constant. That's what acceleration means. So hopefully this gives you at least some feel for acceleration, and we'll be using this model a little bit more as we go on, and you'll pick up more and more tricks.